All right. Morning, good to see you. Welcome back. I wanted to recap yesterday a little bit and then really just kind of let you loose and give you a chance to try some of this stuff out. And in case you did not get a chance to see yesterday's lesson for whatever reason, we are at the point where we are now finding the derivative of something that is the function, right? And so one of the examples that we looked at yesterday was working through the equation of a circle and just trying to find a way to differentiate that, not necessarily worrying so much about trying to get it to like f of x equals or y equals and then doing dy dx, but instead leaving it exactly as it's written and going after it that way. That's what we did, right? We looked at a couple different equations of circles and kind of messed with that. Came up with a halfway decent plan as to how to find dy dx. And what you might see from time to time is that whatever your derivative is, if it's not a function, there's a pretty good chance that we're not just plugging x into dy dx to figure out what the value is. We might plug in y instead, or x and y at a certain point to get there. And so I highly recommend you go back and you check out yesterday's video to see how things went. And the last thing that we did was we actually tried it out on just a different equation. Here on page 250. Okay, so we did 248, 249 yesterday, in pieces, most of them anyway. And then we got to 250 and we tried the one at the top. And what we figured out, I'm not going to do this one again, but this is where I'm going to write the strategy on how to implicitly find the derivative, find dy dx. And as we go through this how-to, what I'll probably do is we can work through the second one as we go. Basically looking at equations that I just cannot get to y equals some function of x, right? Because maybe it's just not a function, or maybe it's just cannot be written that way for whatever reason. What we decided to do that we thought made a lot of sense was to take the derivative, take d dx of both sides. Okay, so let's do that here. Let's take, with the second one here on 250, let's take the derivative with respect to x of the left side. Oh, that's a lie. E to the y, and then d dx of the right. And whatever we have to do to find the derivative on the left, find the derivative on the right, just kind of depends on what we're looking at. Because now we've got everything we need. We've got power rule, product rule, quotient rule, chain rule. We got all our trig derivatives. We know every exponential and log thing they could throw at us. And that's it. Like, those are all of the functions that we've ever looked at. So we've got all the skills now. Now we just got to use them. And what we notice, hopefully, is that right, the left side was a sum, a couple things over there. Right side's a difference, a couple terms over there. And you can really, just like we always have, find the derivative of each one separately. And maybe you find this helpful to write. Maybe you don't need to write it. But what I want you to imagine is this process, right? I'm going to find the derivative of the first one. I'm going to find the derivative of the second one. We'll add those together because it was a sum. We'll find the derivative of x squared minus, right? Just whatever sign connects all of your terms, just kind of bring that along with you, and let's find each individual derivative. Again, I don't know that that step is really super crucial to write down, but that's the mindset that I want you to have in order to take the derivative. Now, if it was a product, sweet, I would use a product rule. If it was a quotient, okay, cool, I'll do that. And as part of our process, as part of finding the derivative of both sides, it's important to look at what you've got and decide, do things match up? Do these variables match, right? The derivative with respect to x of something with x, sweet, that's what I want. They match up, life is good. So I can take that derivative all by itself, and then I'll move on. Okay, so what is the derivative of 2x? And I never needed anything to go with that. because it was the derivative of 2x, it was with respect to x, the variables match, and things are good. But now that I get to the second one, the derivative with respect to x with e to the y, well, if that was e to the x, sweet, e to the x, and I'm good. But the variables don't match. I want the derivative of something with y, but with respect to x. Because I'm trying to find the slope of the tangent line or wherever I'm at, right? I want to figure out how this graph is changing, whatever it looks like. We can take a look at it. It's kind of funky looking. But when those variables don't match, right? Anytime we differentiate a y term, anything that has y instead of x, or in addition to. We've got something that we need to do in order to kind of keep track of what we've got. And the best way to think about it is to have kind of a chain rule perspective. That I can take the derivative of whatever I'm looking at and then, kind of multiply by the derivative of the inside of the exponent, well, whatever we'd have to do, depending on whether it's a polynomial or whether it's rational or it's a log or in this case exponential, right? Treating this initially as if it was just e to the x, but then attaching something to it. Anytime we differentiate a y term, treat it like you would x, like e to the x. Okay, the derivative of e to the x is e to the x. So the derivative of e to the y is e to the y, but I need to attach something to that. Because the variables don't match, it's almost as if I'm multiplying now by like the derivative of the exponent. Just like, if it was e to the 3x minus 4, okay, e to the 3x minus 4 times 3, right? The derivative of the exponent. And that chain rule approach, that kind of application of, all right, well, if I've got something, and now it's not just more than x, it's just different than x. I need to multiply it by the derivative, whatever that is. What is the derivative of y with respect to x? Because that's the exponent. The derivative of y with respect to x is whatever I need to multiply here, right? Because it's e to the f of x times f prime of x. It's just that my exponent isn't some function of x. It's literally just y. How should we write the derivative of y with respect to x? Because that's what we're trying to find. dy dx. Anytime you differentiate something that has y in it, we're always going to attach a factor of dy dx. And that's what we want. Remember what we're trying to do, right? I want to find something that gives me the derivative of whatever I've got, derivative of y with respect to x. It's just that we couldn't isolate y, right? It was stuck in the exponent for the e, plus I've got like a y squared on the other side. There's no way for me to get y by itself. So instead of explicitly defining this as y equals some function of x and differentiating explicitly, we're going to differentiate implicitly, which is just leave the equation exactly as it is and differentiate each little piece. And let's see what we get. Okay, variables match, so I can treat it nicely. What's the derivative of x squared? 2x. Minus, now it's the derivative of y squared. And in my mind, I still treat it as if it was x squared. I just know I have to attach a little dy dx at the end. So differentiate this as if it was just some variable on x to a power, just like we did x squared and called it 2x. What should we call the derivative of y squared? 2y, but we need something with it, times dy dx. Okay, and that's just a chain rule, right? Here's the inside, right? Think of like the y as being inside if you want, right? Drop 2 in front, leave the inside the same, decrease the power by 1, cool, 2y. But then times the derivative of the inside with respect to x. It's just that the inside is y, so the derivative of y with respect to x, sweet, dy dx. And that's what I want. And if there was only one of them, right, if there was only one dy dx in the whole problem, then we would just solve for it. I just move everything to one side, keep the dy dx alone on the other, and we'd be good to go. So that's what kind of step 3 is solve for dy dx. Do whatever you need to get it by itself. If there's only one, go get it, right? Add, subtract, multiply, divide, square, whatever you need to. But there isn't just one. I've got 2. So how do you think we could get to the point where we have dy dx equals, and then everything else? Get them on the same side. So I'm going to move all my dy dx's to one side. So move all dy dx, and I'm going to move it to the left. So that's what this L means. Move it to the left. So I'm going to keep the e to the y dy dx on the left. I'm going to move this one by adding it to both sides, so plus 2y dy dx. And there's my left side. Kept the e to the y term over there, and I moved to the negative 2y term over. Okay. Everything else is going to come to the right. 2x is already over there, so we're good. And then I'm going to subtract the 2 from the left over to the right. But I want to try to isolate dy dx somehow. I need to get them all on the same side and then move everything else over. So move all the dy dx's to the left. So right down here. Everything else to the right. Everything else right. That's a good start. At least we got all our dy dx's on one side. Now what? Factor it out, right? It's common everywhere. So factor that dy dx out. Let's see what we get. Factor. So times e to the y plus 2y equals 2x minus 2. Sweet. So move them all over, factor it out, because now there's only one term, or I guess one factor of dy dx. Let's get it by itself. We just factored it out. We just rewrote the left side as multiplication. Now what? Solving for dy dx. What's the last thing we need to do to get to dy dx equals? Divide it away. Factor and divide. Okay. Divide by whatever's attached to dy dx. So dy dx equals 2x minus 2 over e to the y plus 2y. And we're done. So whatever this crazy thing looks like, there's a way to stop anywhere you want. And look, there's an x and 2 different y's in that equation just to be able to take a look at the derivative, figure out how this graph is changing. Let's see, 2 to the x plus e to the y equals x squared minus y squared. Funky looking. That's pretty cool. Here, let me erase this stuff. Nice. That's cool. That's right. Nice. Okay. And obviously this isn't a function, right? It's never going to pass the vertical line test. There's some spaces where things are undefined. That's cool too. There we go. Cool. And that's it. That's the whole process. Differentiate both sides. Do whatever you need to do to get to y with the x by itself. Let's do one more together, and then I'll give you a chance to try it. Today, maybe even tomorrow, we'll see. I don't know how much time you think you need, but how much practice you think you need. I want to get into the second half of this first half. So I want to get into the second quarter of the chapter by the end of the week for sure. So let's do it. Let's do it. 2xy equals 3y squared plus 2x. I got a y squared term, and I have an xy term. There's no way ever for me to get y by itself. And I don't even have to. I don't even have to think about doing it that way. Even if there was a way to get y by itself, maybe that's just as much work as just doing implicit differentiation and taking the derivative of both sides right away. 2xy. And then d dx of 3y squared plus 2x. And the reason I say, hey, you know what? Maybe you can get y by itself. Like, look ahead for a second. Just factor out y on the right side and divide away 2 minus 3x squared. You're there. You can get to y equals. Maybe that's helpful. Maybe that's just as much work because now I have a quotient. I got to use a quotient rule. Right, maybe you just say, you know what, I'm just going to go for it. I'm just going to find the derivative right away. That's totally up to you. You have the ability now to differentiate right away without having to rewrite anything. Okay, so now let's look at the left side. 2xy. What are we going to need in order to differentiate? 2xy. What type of derivative rule is going to come into play here? Product rule. It's a product, right? 2x times y. Right? U is your 2x. V is your y. U is 2x. Sorry, what is that? My goodness. Something down here. U is 2x. So du is 2. V is y, so now dv. Remember, when we first looked at product rule, quotient rule, chain rule, remember that when we found du, I said, all right, listen, I know we're just going to write du, but it's really du dx. Right? We're going to find the derivative of this with respect to x. Same thing for dv, right? Yeah, I'm just going to write dv, but what is it really? It's dv dx. And so what's the derivative of v if it's equal to y? 1 times dy dx, right? The derivative of whatever it is, as if it was an x, times dy dx. I'm just going to call it dy dx. There it is. That's my little side work that's going to help me find the derivative of the right side. And the product rule is going to make that happen. U dv plus v du. 2x times dy dx plus y times v du times 2. Sorry. Times 2. Perfect. Now, I think we're at the point where it's okay. All right, so I got 3y squared on the right, and I've got the plus 2x. I got to find the derivative of the whole right side, so let's just find the derivative of each one separately. The derivative of 3y squared, treat it like you would 3x squared, and then we'll just attach a dy dx to it. So what does that look like? 6y dy dx. Perfect. It's just the chain rule. Inside is y. That's all it is. Derivative of 2x. Go ahead. Solve for dy dx. Can you get it isolated on the left and get everything else over to the right? Not going to stress about the order that you write things in. Whatever works for you works for me, so I got some flexibility there. Where is it? 1. 119. Get to there. That's good. Now let me ask you this. Can we divide these y's away and make things a little simpler? Let me ask you a question before you answer that. Is y a common factor, top and bottom? So let me re-ask the question. Can we divide those away? Please stop doing that. Happened way too much on that 3.2 quiz. Way too much. Okay, people were taking like 2x minus 1, which was just like a term, a collection of terms. It's a binomial. It's part of a much larger numerator and denominator. People were dividing things away that they had not factored out yet. You cannot divide things that aren't being multiplied. Okay, you got to be on the same level, right? We want to get on that same level. So what could we divide away? Because it is a common factor, both top and bottom. 2. There is a 2 everywhere. There's not a y everywhere. And if it helps you to see this, do not just start dividing things away until you've factored. Okay? Rewrite it factored first. Factor first, simplify second. Very good mantra that I start teaching in like algebra 1, because now those 2's can go away, and there's our derivative. 1 minus y over x minus 3. Again, more than one y in the problem, x and y in the derivative. So nice to be able to look at whatever this craziness looks like. Let's see. I'm always curious. 2xy equals 3y squared plus 2x. Funky. Again, not a funky, right? Getting into the land of the sideways hyperbole and doing all sorts of fun stuff. So looks like a path of a boomerang or something. Like a boomerang. Okay, so we needed the product rule in order. And you'll see that in the one on the bottom right as well, and that's the one I want you to try first. Before we move on and try anything else, I want to see if you can do that last one, bottom right. Because you'll see on the right side, as part of your derivative for one of them, you're going to need the product rule in order. Okay? But a big plan to make your life easier is to try to make the process as simple for you as you can by looking at each term separately. Find the derivative of 5x cubed, find the derivative of 3, find the derivative of 2y, find the derivative of 3x squared. All right, so give this one a shot. Looking back often at the one we just did in case you feel like you get stuck somewhere. make sure you get to here for me 3 lines in before you start solving for dy dx. I don't want you to make a mistake early and then it just compounds itself the rest of the way. Anybody have issues getting to here that we want to address? Okay, then I'll start solving. Now, dy dx can be on either side. I always say move it to the left. We're already all on the right, so that's kind of up to you. You can kind of write it however you want. I guess I'll save myself a little trouble. Just keep it over there. Because equations can be flipped around if we want. And I'll flip it back. Okay, we're going to skip ahead just so we get a little more practice before we work on some of the more advanced stuff. So go to 252. Just for the rest of today, try those 4. When you've done those 4, we've got enough practice for the day. And then we will try to do a little bit of, I don't know, pushing ourselves a little bit further tomorrow with this implicit stuff. And then Thursday will be probably a big important day for us because we're going to use this implicit to do something that's very, very, very important in terms of your calculus knowledge. So now I'm not going to be here on Friday, just to remind you. Okay, I'm not here this Friday. Baseball's in Grangeville, so. So you have a sub here. I just want to make sure that I get things started. Hey, and if we can even get things started on Wednesday, then we keep it better. I don't think we have homeroom on Wednesday. I think it's back to like a regular schedule, so that's good. Because it's the last week for seniors, I think they saved us a little bit of trouble. Quiz 3.2 making its way back around. Anything in the B range got a sticker. Anything in the A range got a smelly sticker. If you have a peppermint looking thing, then it smells like peppermint. If you have a dinosaur, it smells like strawberries.
Quarantine did this to me. That's why
You gotta get it done.
I do. The thing is, I know I'm running into stuff that I didn't see.
Yeah. So let me know what you need.
I'll watch back.
Those grades will go in today at lunch. Haven't put those in, or maybe even third, because I crossed out third. I'll have some downtime. So if you want to take a look at that quiz sometime before you leave and ask questions about anything that comes up there, if you got stuck on something, lost points, you're not sure where, can't read my writing, whatever the case may be. See You Succeed trade to final grades are starting to update as I look back through partial credit, which there was a lot for the first handful or two people. So that's, yeah.
I was just wondering, because I did like really bad on that. Do I like have to have it on my course transcript?
Your grade that is going to go to CU is the grade that you get in here. The only grade that's ever going to be reflected in your college transcript is the grade that I give.
Okay, that makes sense.
The score on anything is hidden. It's just, how did you do in the semester? That's it. So don't stress it. Don't stress it. Yeah. I think a few of us were a little bit surprised. Yeah.
Life was really like a C or D range.
Yeah.
It's late.
Well, do the best you can, and I won't let it destroy you. Just get it done, though. If you don't get it done, then it will hurt you. But if you get it done, we'll be all right. So I have Zyla, Alora, and Megan. I have your physical copies. If you want to pick them up this week, whether you're quarantined or self-quarantining or just not here today, and you want the copy, just come grab it. All right, I'm going to do 252. See how it goes. Hopefully the first one starts off easy for you. That's why I wanted to do this before we went too crazy. There are negatives everywhere, so I just got rid of those. I could have avoided that by moving all of my dy dx's to the right, and then the 6x squared to the left. Either way is fine. Here I'm going to take my time, help myself realize that this d dx in the middle is going to need product. If you have gotten to the point where you do not need to write down u equals v equals du and dv, that's fine. Okay, that's just a level of comfort you want to find once you're ready. I usually just kind of do it in my head. U dv plus v du. Careful with the subtraction there, though. I say it out loud and then I still put plus. There we go. Run out of space, so I'm going to factor at the same time. I keep it in a nice order, putting the 2y first and then the negative x. I'm going to slide this over. Doesn't matter what order you put it in, so don't stress that too much. 2y dx. So there's 1 and 2 on 252. Anybody have any questions about the quiz? Let me know.
Well, I
Yeah.
got a bunch. Since I missed the exponentials,
Mhm.
don't have the bases and the logs.
So what I'm going to do, and this is not just for Sven, I'm actually going to send this out to everybody. I'm going to send you this document that I put together that has all the derivative rules on it. And Sven, on there, you'll see once you get onto the second page are all of the exponential, I know it's hard to see behind all the work, but all of the exponential and log shortcuts. So you have all of the rules laid out for you. Okay, because the last thing on here is implicit, and now we're finally there, so we're good. Take d dx at both sides. Anytime you differentiate a y term, attach a factor dy dx. There's only one, solve for it. If there's more than one, move them around and get it by itself.
That'll help me.
Yeah, for sure. So let me do that today. I will just share it with you like through your drive. So it'll be sitting in there waiting for you. Number 3 looks like we're going to need the product rule twice. And x squared y is going to need the product rule, and then y squared x, that'll need its own product rule. But I'll leave these two up just for another moment. And then I'll do 3 and 4 and then and yeah, we might just jump right into some stuff tomorrow. Now I know that this week and next week is AP testing, so I know a lot of us will be missing some time here and there. So just like you guys did this morning, just let me know if you have things scheduled, just so I can anticipate whether you'll be here or not. But I'm still expecting you to play catch up a little bit if you can that night. I won't assign anything for you to do outside of school. Of course, knowing that whatever your AP test, of course, takes precedent over everything else for that day. But trying to keep up for sure. Tomorrow and Thursday, I think, are going to be 2 big important days for us where we start and practice the application of implicit differentiation on actual real applications of things, which is what the whole chapter is all about. So we'll see how that goes. With us being a little short on time, we probably won't master chapter 4 ideas, but seeing them and getting a chance to try to get better, I think is going to be helpful, because I definitely want to get to the second half of chapter 2, of chapter 4. Looking at second derivative stuff, talking about, if I can, we'll see if it comes up. I don't know if it's a chapter 5 thing, but position, velocity, and acceleration, some physics applications of calculus, because calculus without physics and physics without calculus, it's like the sun without the moon. It's just they're so intertwined. It's so nice especially if you take physics at all. I didn't take it in high school. I ended up taking it in college, but there's actually a calculus-based physics class that's so much easier. That's all it is. Calculus is the study of change, and that's all physics is particles changing in space. So, all right, let me do these last couple because we only have about 10 minutes, a little less. But if there's something you don't get, you gotta speak up today, because tomorrow I'm going to expect you know what you're doing with implicit so we can use it. So if something about what's happening so far is just not working for you, let me know. I'm gonna start to break things up here right away, just so I can kind of visualize my U and my V a little easier. But again, I'm at the point where I'm not writing it down anymore. I feel okay just saying U dV plus V du U dV plus V du. Maybe you can factor and simplify at the same time. Maybe you can factor and divide. Awesome. Works for me. If you see anything in common, divide it away. If you don't, then you're done. Work slower than me? Great. You want to work faster than that, you better be on the money. That's about as fast as I would ever go. Maybe I wouldn't write the first step in blue, I would just start differentiating. That's the only way to go faster. Parentheses aren't really necessary now because things are just being added, so that's okay that you don't include those. But they're there just to make me kind of isolate certain derivatives so I can pinpoint how things are going. Kind of looks like a nose. That's kind of funny. Arches. All right, so for me, this is where U and V split. Product rule again. 2xy, two sine of x is going to be my U. Cosine of y is going to be my V. Let's go slow so we can see it. There's U. So du is nice because the variables match. V is cosine of y. So the derivative needs a chain rule. Negative sine y times the derivative of the inside. So there's my d dx. U times dv plus v du, and the derivative of 1 is 0. Blow this up a little bit more. Let's clean it up first. Let's see, negative. Not that I really need to, but just so I know what I'm looking at. Negative 2 sine x sine y dy dx. Plus 2 cos x cos y equals 0. Nice. So that's the cleaned up version of the same thing. Hey, only 1 dy dx. That makes life easy. Line it over. Divide it away. I'll take my time so you can see how the simplifying is going to work. Over negative 2 sine x sine y. Okay, let's see. How can we make this look real nice? Well, we've got some cosines over some sines, right? Absolutely. We just want to make sure that the insides match, right? Whatever is inside. Because if I can't do like cos y with sine x, right? Those don't go together. But like the negative 2's are gone, so that's cool. All right, so that worked out nicely. And then cos x over sine x, that's cotangent of x. And then cos y over sine y, that's cotangent y. Yeah, for sure. Let's use some cotangents, make things a little bit easier. That is a weird, terrible looking dy dx. Let's make that nice. Dy dx. And there we go. There's 252, all nice and pretty. Let's see, what do you think? Are we good? We feel okay about implicit? Maybe you're not a master yet, you'd have to look back at some other things, but if you feel like you've got it down pretty well, maybe we skip ahead right away and get to the good stuff. I think that's a good idea. What you'll notice though, if you want right now, just kind of flip in the next couple pages, even the next one. Now look at number 5. Find the coordinates where it's got a horizontal tangent. Find the coordinates where it's got a vertical tangent, where we take the derivative and set it equal to 0, or we figure out ways for it to be undefined. There are some good ways for us to not necessarily apply it to like real life functions just yet, but kind of pinpointing some spots along the way that are nice to look at. Find the equation of a tangent line, equation of a normal line, they give us the point, they give us the function. The 2/3, that's definitely a cusp. Let's see what that looks like. They love that one. X to the 2/3. Okay. Anything that looks like this. Okay. These kind of functions. The value exists at 0, but the derivative is undefined. Okay, because imagine like taking the derivative of y equals this, dy dx, exponent in front, decrease the power by 1, that's 2 over 3 cube root of x. Can we plug in 0 into the derivative? There's your function, there's your derivative, right? Function is defined, derivative is not. Okay, so if you see, it's called a cusp. Okay, that right there, okay, called a cusp. Kind of like, imagine like bouncing a ball. Okay, it does not bounce like a parabola, it's going to come down, bounce, and then head off in the direction it came. Maybe you can tell what's happening just thinking about the tangent lines that we would draw along the way. -2, -5, -10, -20, -1,000,000. And then all of a sudden, +1,000,000, +10, +5, +2, +1. The limit of the derivatives are undefined. As it goes from super big negative to super big positive, there's no consistency there, there's no continuity. So if we want the derivative to be defined, we need the derivative to be continuous, which is kind of interesting. But it is definitely not at a point like this. So we want to watch out. I think it was x cubed, x to the 2/3 plus y to the 2/3 equals something. 5. Let's see. Oh, there we go. I'll leave you with that one. That's pretty good. Thank you. Yeah. Have a good day, everybody. I will see you tomorrow. Hi. What do we think? Is she gonna come around?
I think you should give me a bill, just
Just
spice it up a bit.
I know, but that would at least get you to come back for one more year.
That's true.
What's up, John?
I'll be here Thursday.
Cool. Ooh, A push. There's a class I avoided hardcore in high school.
I wish I.
All right, good luck. So you'll see, like Thursday will just be a practice day probably with what we do tomorrow, which is all implicit. It's just we implicitly differentiate volume, surface area, like we're actually going to do stuff with it. So you'll see tomorrow. You good? Maybe, maybe not. Just do it and get in, baby. Good things left.
I'm gonna try as hard as I can, but stupid April card.
I know, I
That's
know.
what killed people.
This is the extra?
Yeah.
Okay, then
I will not be around Thursday.
good luck. You're all good. Thanks, buddy.
Nice.
All right. I got a
Thank
pen
you.
here. Let's see.
Did I tell you what happened to my brother with baseball? He broke his hand.
Who's your brother?
My brother, so he's in middle school, so
Okay.
he's not in high school, but I feel so bad, but he's going to every game, I'm like, good on you, buddy.
How did you break it?
Playing,
Playing?
yeah, he's like, so he went to go pitch one of the fly balls or whatever.
Yeah.
But it was like, his hand was right next to like the base, like this.
Oh.
And a kid who's twice his size comes sliding in. Luckily, it's not broken again, it's surgery, but like, oh my God, I feel so bad. So you're playing tomorrow, not tomorrow, Thursday, Friday.
Friday morning. I'm leaving. So we played 2 games on Friday. One against Grand Junction Central High School, one against Fruta, and then Saturday we'll play.
Wildest thing I've ever heard of.
Well, no,
We're
I'll
supposed
have
to
to
play
play
yesterday. We're
that.
supposed to play today.
Good show.
We'll be back home next week. I think we play Shap at some point.
Well, I'll have to come back just to know how it goes.
Okay,
I'm
great.
curious. Well, have a good day. Thank you so much.
What's up?
It's
Might be interesting to work today. Let's stop this.